Hello and welcome to Tech Simplified TV. We all know CMOS manufacturing is a huge task. A small amount of process parameter variation can lead to significant variability in device performance. In today's episode, we will talk about variability. We will discuss how variability at different stages of CMOS manufacturing impact the final performance of the circuit, how variability leads to process corner creation, and how we model them. So, if you are interested, stay tuned till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, challenges to build CMOS. Second, variability and level of abstraction. Next, process variation. Next, voltage and temperature variation. Next, design corners. After that, sources of process variations. There are 2 slides on this topic. After that, impact of process variations on carrier mobility. Impact of process variations on gate oxide capacitance and threshold voltage. Impact of process variations on W and L of MOSFET. Impact of variations on yield, delay, and energy. Next, analysis methods for studying variability. And finally, modeling variability. So today we will cover all these topics to understand impact of variability on device performance and the reasons which contribute in variability. So we are done with this slide. We will move to the next slide. Challenges to build CMOS. In today's era, we fabricate millions of transistors. Fabrication of such huge number of devices flawlessly is a tough task. So it is challenging to fabricate millions or billions of transistors which will work flawlessly for 10 to the power 18 cycles. We have to fabricate in a way so that the transistors work reliably. They will perform as they are intended to work, and that it will do continuously for huge number of cycles. That's the biggest challenge. Now, transferring exact shape to silicon wafer or creating uniform doping profile are challenging. VLSI is basically a concept to reality process. First the concept, then the design. Design is transferred on the silicon. A transistor is basically transferred on silicon by layout, and layouts are geometrical structures. So suppose on pen and paper or on software, this shape has to be transferred on silicon, although when it's transferred on silicon, it doesn't remain same. Transferring exact shape to silicon wafer, that's a challenge. Another challenge is maintaining uniform doping profile. When we see the cross section of a MOSFET, we see that this part is source, this is drain. So these are the highly doped zone and this is very lightly doped zone. So this doping profile, although in this zone it's not very uniform. In this zone it's not very uniform. This uniform doping profile creation is a challenge. These are basically practical challenge when we are fabricating or developing the chip by individual steps. Now, operating condition might range from freezing to boiling. So first 2 are manufacturing related challenge we have mentioned. Now it's operation related challenge. Functional chip, now it's in operation and the condition in which that chip is getting operated, that is not fixed. Temperature might range from freezing to boiling. Intense electric fields gradually break down the gates. A chip is getting used for longer times. Continuously electric current is flowing on gate. Continuous voltage is applied. Intense electric field can gradually break down the gates. Continuous flow of current carry away atoms of wires. That is electromigration. Now, another issue is cosmic rays zap the bits stored in a tiny memory cell. Memory cells are there and each of them have some bit stored in that. So a stored bit can be changed because of interference of cosmic rays. That could be a challenge. Another is manufacturing or environmental variation has impact on chip. This temperature is going up, down. Continuous electrical field is carrying away the atoms of the wire. So basically structure of wire or interconnects getting changed. So all of these manufacturing variations, environmental variations, this all has impact on chip. They have impact on individual MOSFETs, and overall these impacts sum up and manifest or come out in front of us as impact on performance. Now design must include impact of manufacturing variations and changing operating conditions. So there are three different sources of variation. First is process variation P, supply voltage variation, and operating temperature. So P, V and T. We all know that because these P, V, T or P, T, V corners are mentioned. These are basically this variation of process, supply voltage and operating temperature originates from there. Our aim is to design a circuit that operates reliably over all extreme P, V and T. Otherwise, this can cause poor yield and circuit performance. If we do not consider variation or impact of this variation of P, V and T, that could lead us to poor yield and circuit performance. So these are basically challenges to build CMOS. We are done with this slide. Now let's move to the next slide. Variability and level of abstraction. So here is a diagram. We have used this diagram to understand what is happening. This is the basic process. The process we use to fabricate chip, such as oxidation, requires heat, ion implantation. And in case of ion implantation, ions are implanted on the wafer with high energy and dose. Lithography. Lithography is transferring a shape on the wafer. Now chemical mechanical planarization. These all are the source of process related variability. Now temperature might vary, dose that might also vary, and energy, a slightly difference can impact the process. Wafers are processed in batch. In one batch, fixed multiple numbers of wafers are processed. These are called lot. We will see in some later slide. In second lot, while doing this ion implantation, suppose the dose or energy is slightly different from the previous lot. And if we suppose that in one lot, n numbers of wafers are processed, so first batch of n wafers are processed, especially ion implantation for those n number of wafers has been done with some dose and energy specification, and for next batch of n wafers, this ion implantation has been done with dose or energy slightly different from the previous run. So this ion implantation, how much these ions penetrate and where it would have the highest concentration, how many numbers of ions will be implanted, that might get changed because of this change, because these ions are activated with energy. That's why they move and penetrate and go into the wafer. So if that energy is changed, the profile might get changed. And accordingly, when wafers from these two lot perform, their performance might vary. Due to process, here variability get introduced in the device. Now, random variation in operating conditions such as temperature and the power supply voltage VDD increases with circuit clock frequency, leading to circuit performance variations. We are talking about when the circuit is in operation. This degrades yield and increase production cost. So from one to another, this gets changed. Now, variation of performance metric of a circuit like delay, dynamic power and static power consumptions ultimately propagate their negative influence on overall performance of a chip. So, this temperature, dose and energy, they make process step in one run to different from the second run. Process variation parameters contribute mostly in case of device structure and doping profile. That means the basic parameters or basic behavior of the device is slightly different from the other, along with the environmental factors that basically decides the device characteristic. And this device characteristic along with this temperature, VDD, that is environmental factors, that decide the circuit characteristic, and overall circuit characteristic with environmental factors controlling the chip behavior or deciding the chip behavior. And overall, if this device characteristics or circuit characteristic is hugely deviated from what we have expected, that actually impacting the yield, and if yield is bad, so cost is high. So we are done with this slide. We will move to the next slide. Now process variation. Here we can see lot to lot variation, wafer to wafer variation, chip to chip or across wafer variation, and on chip variation. So we will now understand what are these things. So process variations can be classified as lot to lot, that is L to L, wafer to wafer, W to W, die to die, that is D to D, inter die, or within wafer, that is WIW, and within die, WID or intra die. Now let's understand in a little bit detail. Lot is batches of wafer. Usually wafers are fabricated in batches. So in one batch, n numbers wafers are processed. That is one lot. Once it's done, then another lot is done. Each one has n number of wafers. And we always try to maintain same physical condition. Same temperature, same energy, everything. Still, so this die is different from this die or from this die because of process variation. This difference or variability between two lot, we call it lot to lot. Now wafer to wafer. Let's concentrate on one lot. Even in one lot, two wafers, these dies, they have variability. So this is called wafer to wafer variability. Now die to die. Now let's concentrate on single wafer. From this wafer to this wafer, the same position, same die is different from this to this to. Now die to die. In a single wafer, so many dies are there. So this die is different from another die. That is die to die or inter die or within wafer. Inter die between two dies on same wafer or within wafer. This one. Third. And fourth one is within a die, there are huge number of MOSFETs. One MOSFET is different from other. That is on chip or intra die or within die. These are four types of variation. So variability in lot to lot, wafer to wafer, and chip to chip are almost equally applied to every transistor on chip. These inter die variations are called global variations, and remaining within chip or intra die variations referred as local variations. And these three are global. That is lot to lot, wafer to wafer, and chip to chip. These are global variations and this is local variation. Now global and local variations must be modeled accurately. That helps in estimating the power and performance scaling of the circuit complexity. During analysis, we must model this variability. Otherwise, we can never estimate the yield or performance. That estimation will be wrong. So local variations get averaged out for large number of transistors or long critical paths. And global variations usually add up and shift the average power performance of the entire chip. Now D to D or die to die variations make one chip faster, slower than another. And within die or intra die variation become important in nanometer processes. So this one is very local thing is very important for nanometer processes, and die to die variations mean one chip faster or slower. So we are done with this slide. We will move to the next slide. Now voltage and temperature variation. Systems are designed to operate at nominal supply voltage, but this voltage may vary for many reasons, including tolerance of voltage regulator, IR drops along supply rails, and DIDT noise. Typically, the supply is specified at plus minus 10% around nominal at each logic gate. In case of supply voltage, it's defined like 5 volt plus minus 10%. We define it in that way. The supply varies across the chip as well as in time. Speed is proportional to operating voltage VDD, and this leads to plus minus 10% delay variation. Speed is proportional to VDD, and this supply voltage which is coming as a VDD that has 10% variation. Speed is also 10% variation. So opposite of speed means delay. If speed is high, that means delay is less. If speed is less, so delay is high. So delay, in other terms, delay is also getting varied by 10% plus minus. As temperature increases, drain current decreases. The junction temperature of a transistor is the sum of ambient temperature and the temperature rise caused by power dissipation in the package. This rise is determined by power consumption and package thermal resistance. Junction temperature of a transistor is the sum of ambient temperature and temperature rise caused by power dissipation in the package. Packaging. It's not only fabricated, it need to be packaged properly. Junction temperature transistor is sum of this ambient temperature and temperature rise caused by power dissipation in the package. And this rise, how much this temperature of that chip will rise, determined by the power consumption of the total circuit, and the package thermal resistance. So ambient temperature ranges for parts specified to commercial, industrial and military standards. So use for which purpose the chip is getting used according to that this specification that are mentioned. Like here is a chart. So standards are commercial, industrial and military. Commercial is minimum 0 degree, maximum 70 degree. Many industrial processes temperature is higher temperature than normal operation. So usually commercial is minimum 0 degree and maximum 70 degree mentioned. Industrial minus 40 degree, 85 degree. In both cases, the range in industrial is wider compared to commercial, and in military is the harshest condition. The highest range is provided for military application. Now temperature varies across a die depending on which part dissipate the most power. The variation is gradual, so all circuits in given 1 millimeter diameter see nearly same temperature. Temperature across a die also varies depending on which part dissipate the most power. The variation is gradual, obviously. So the circuit in a given 1 millimeter diameter see nearly same temperature. This is about voltage and temperature variation. We are done with this slide. We will move to the next slide. Design corners. The collective effects of process and environmental variation can lumped into their effect on transistor. Typical, that is also called nominal, fast or slow. T, F and S. When these processing variations are combined with environmental variations, we define design or process corners. The term corner refers to an imaginary box, this one, that surrounds the guaranteed performance of circuits. The corners are specified with 5 letters describing the NMOS, PMOS, interconnect, power supply and temperature respectively. The letters are F, T and S for fast, typical and slow. Fast, F, typical T and slow S. So basic nomenclature, NMOS can be slow, typical and fast, that is S, T, F. PMOS can be slow, typical, fast, that is S, T and F. Next, temperature can be hot, typical, cold. If temperature is hot, device will be slower, so it is S, typical and cold, so fast. VDD can be high, typical, low. If VDD is high, that is fast, typical T, and low, that is slow. Example of process corners and their detailed descriptions. So example of process corners and their detailed description. Process corner label may include NMOS, PMOS, temperature and VDD. So T means typical NMOS. First one is NMOS, then typical PMOS, then T means room temperature, that is typical or nominal, and then T, nominal supply, and this SSSS means slow NMOS, slow PMOS, temperature slow if it's hot, so hot temperature, and low supply. Supply is low, that is S, so low supply. FSSS, that means fast NMOS, slow PMOS, slow temperature means hot temperature, and slow supply means low supply. So we are done with this slide. Let's move to the next slide. Now sources of process variations. In first two slide we have mentioned these steps include variability. Now let's see how it happens. Lithographic variation. Uniformity of a printed feature size depend heavily on control of the lithographic imaging system. A small vibration in the apparatus can lead to non-uniformity of the critical dimension of printed lines and significantly change the speed and leakage of CMOS transistors. In FinFET episode also we have mentioned that lithographic variation means typical wavelength is coming out from the machine and it's transferring a shape on the wafer. Small vibration in the apparatus can create a non-uniformity. Now lineage roughness, it is deviation in feature dimension from intended shape, arises from variation in lithography and etching process. If this one is the intended shape, perfect rectangle, when it's transferred it's like this, deviation is there. If we take it as a mean position, then this way, that way, this way, that way, it's moving. Now random dopant fluctuation. Random dopant fluctuation refers to the random microscopic fluctuation of the number and location of dopant atom in the MOSFET channel region. It causes fluctuation of transistor electric parameters such as threshold voltage, short channel effect and drain induced barrier lowering. Dopants are here, although they are fluctuated, their positions, density is not same across all position. Here the density, here the density, all are different. This is not same, not uniformly distributed. That is dopant fluctuation. Numbers and location of dopants in the channel region, not uniform. So RDF, that is random dopant fluctuation, is also another cause of variability. Now let's move to the next slide. Sources of process variations: well proximity effect and STI and length diffusion. Advanced CMOS technology use high energy implants to form deep retrograde well. During implant process, atoms can scatter laterally from the edge of the photoresist mask and become embedded in the silicon surface close to the well edge. This is the resist so that the implant doesn't come here. We need to protect this area. We are forming this well. They are getting scattered and their direction is diverted. Vertically also coming and scattered also coming. So here effective density became higher. We have tried to show it with shading, color shading. As a result, well surface concentration changes with lateral distance from mask edge. This is the edge of the mask. From here, this density changes because here both from vertical direction implant is coming and the scattered implant is also coming. So in this zone the concentration is higher over range of 1 micrometer or more. As a result, well surface concentration changes with lateral distance from the mask edge over range of 1 micrometer or more. Threshold voltages and other electrical characteristics also vary with the distance of the transistor to the well edge. This phenomenon is known as well proximity effect. Here, implant concentration, surface concentration is changed, and accordingly the parameters like threshold voltage, other electrical characteristics, that also vary with the distance of the transistor to the well edge. Now STI and length of diffusion. Shallow trench isolation and length of diffusion. STI is forming trench and filling it with non-conducting material to isolate active regions. So this is one device, this is another device. Here shallow trench isolation is done to isolate from this to that. These filling materials exert compressive stress to vicinities, compress this area. Tensile stress or compressive stress can change the mobility in silicon. So that is basically mechanical strain. Mechanical stress is there. So this filling material exert compressive stress to the vicinity, that is in diffusion areas. In diffusion areas they give stress. This stress is commonly referred as STI stress, also called length of diffusion effect, where the characteristic of a device vary according to the distance of its gate from the diffusion edge. Mechanical stress change free carrier mobility. That is the basic principle of strained silicon. Using mechanical stress, actually silicon is strained and mobility changes. We have came across this thing in strained silicon episode. So consequently, transistor with same gate size but a different LOD have very different speeds. The stress increases as the channel to STI active edge distances decreases. Channel to STI distance, depending on that distance, the amount of stress is changed, and amount of stress is changed means impact on free carrier mobility is changed. So one transistor always behave different from the other. So that is STI and length of diffusion effect. So we are done with this slide. We will move to the next slide. Impact of process variations on carrier mobility. So the MOSFET parameters are affected by relevant process step. A single process step can affect multiple transistor parameters. Decoupling the effects of one variation source from another is extremely difficult. Look at this chart, we can easily understand that. Mu, that is mobility, is impacted by ion implantation, diffusion, annealing and stress. Gate oxide capacitance is impacted by gate oxide formation. WNL, that is width and length, that is impacted by etching and lithography. And VTH is impacted by ion implantation, gate oxidation, annealing, etching, lithography. So lithography is mentioned here and here also. If we consider length and width, etching and lithography both has contribution in that. In case of change of mobility, ion implantation, diffusion, annealing, stress, multiple steps contribute in that. So segregating or decoupling which one is affecting is really difficult. Now let's see how carrier mobility is impacted by process variation. Mobility is the ability of carriers, or that is both electron electron and holes to travel through the channel of a MOSFET with an applied electric field. Mobility of carriers in channel is impacted by doping concentration since it determines the mean free time between collision. So mobility is ability to travel through channel under electric field. Now, if doping is higher, number of dopant is higher, that is channel area is more crowded, mean free path decreases. Mobility of carriers is impacted by doping concentration since it determines the mean free time between collisions. The dose and energy of ion implantation and annealing temperature directly influence mobility since these process steps primarily determine doping concentration. Dose and energy of ion implantation and annealing temperature directly influence mobility. Now, strain engineering of a device channel either by using local techniques such as nitride liner and silicon germanium in source drain or global techniques such as silicon germanium substrate affect the device mobility. We know strain can change. Unintentional stresses induced due to STI can cause intra-die mobility variations of few % depending on transistor distance to the STI edge. Just in last slide we have discussed that. Introduction of strain can change. That is also a variability one device to another, from one circuit to another. Dose, energy and ion implantation, all these impact the carrier mobility. Doping also impact carrier mobility. Now introduction of STI, which is very important step, important for isolation, that creates unintentional stress. All these parameters, they affect the carrier mobility. So we are done with this slide. We will move to the next slide. Now gate oxide capacitance, COX and threshold voltage. Gate oxide thicknesses are scaled to atomic level on order of 5 atomic layers, that is 10 angstrom. A small change in one atomic layer can greatly impact on not only oxide capacitance but also the threshold voltage and mobility of MOSFET device. A small variation in thickness of just one atomic layer would result in 20% variation in gate oxide thickness. Controlling this variation is difficult due to physical limitation at this atomic scale. In state of art or nanometric devices, this impact of variation is impactful because already device dimension is reduced. This gate oxide thickness has scaled to 5 atomic layers, that is 10 angstrom. A small variation in thickness of one atomic layer results in 20% variation. So that's huge impact. Now use of high K dielectric material as good gate oxide results in moving to a new gate oxide material not only reduces gate leakage current but also reduces the impact of variability on COX due to much larger physical oxide thickness. However, variation in oxide of high K stacks interfaces are still problematic and can also affect performance. Now high K stacks are also there. Handling high K stacks is also problematic. So now threshold voltage. Threshold voltage determined by number and location of dopant atoms implanted in the channel or halo region. Ion implantation is a stochastic process leading to random dopant fluctuation that causes VTH to vary. Impact of statistical distribution become even more significant as device dimension reduces. The variations have become large in nanometer process because the number of dopant atom is small. When the dimension is small, a small change in number of dopants can give a huge impact. So this variability actually impact gate oxide and threshold voltage. We are done with this slide. We will move to the next slide. The impact of process variations on W and L. Transistor dimensions. So the saturation current shows that the width and length of transistor influence the device current. Processing steps and related factors like the wafer mask, exposure time, etching process, spacer definition, source drain implantation and even the environment during the manufacturing process contribute to the overall variation in gate length and width. Any variation in channel length is directly reflected in device delay, which is directly proportional to the channel length. Here ID is proportional to W and inversely proportional to L. So shrinking of device channel length is physically limited by patterning wavelength, where lambda is 193 nanometer for 45 nanometer technology node. Therefore, patterning a very short channel length below this wavelength become extremely difficult to control, leading to an increase in gate length variation. If we scale down the device dimension, accordingly we have to scale down other things. The patterning wavelength, which is used for 45 nanometer technology node, that is 195 nanometer wavelength. Patterning a very short channel with this wavelength is difficult and variation get introduced there. On and off current. From this current we can easily understand that W and L is always related to the current. So both on and off current has dependency on L and W. So small change in process variation causing variability in L and W finally result in transistor performance variation. If transistor dimension changes, since I on and I off, on and off current has a dependency on this dimension L and W, definitely that will get changed. So I on and I off also impacted with process variability. We are done with this slide. Let's move to the next slide. The impact of variations on yield, delay and energy. In CMOS, yield indicates the fraction of products that are operational. It is probability that a particular product will work. So failure probability is expressed as x equal to 1 minus y. Design techniques and analysis tools are used to minimize range of variability. Variability more than permissible range cause failure and thus yield reduces. At each node, dimensions get smaller and thus a constant variability actually means greater percentage of change. Small percentage of variability create larger impact in this dimension. Variability more than a permissible range considered as failure. At each node, dimension is reducing and variability remains same, then that is a huge impact. That's a huge percentage. So small percentage of variability at one node can create huge impact next advanced or smaller node. Now delay. A change in on current changes the delay of an inverter by the same fraction. An M input gate will have up to M transistors that can vary separately. Suppose a circuit is there where M numbers of inputs are there. It's an M input gate and M transistor that can vary separately. The delay of N stage path is sum of delays, and these in this system there are suppose number of stages are there. Number of input is M and number of stages are N. Suppose here like these stages are there. The delay of N stage path is sum of delays through each stage getting added. Delay gets added. Now if the variation are completely correlated, the delay of path will have same variance as the delay of gate. However, if the variations are independent, the variance introduced by factor N cross M. Number of input is higher, all of them are varying separately and stage is N and delay is getting added. So altogether this variance becoming a huge. So delay of N stage path is sum of the delays through each stage. If the variations are completely correlated, the delay of path will have same variance as the delay of gate. However, if the variations are independent, the variance reduces by a factor of N cross M. Now energy. Variation has a minor impact on dynamic energy. It has major impact on static leakage energy. Static leakage energy is exponentially sensitive to threshold voltage. Systematic variation in VT makes a tremendous impact because all transistors are correlated and exponential as a long tail. Variation has impact on yield, delay and energy. We are done with this slide. We will move to the next slide. So what are the analysis method of studying variability? Variability is there, we know, and we must analyze them properly to include in our modeling so that their impact is included. Digital circuits are designed in a way so that circuits should meet the performance specifications such as speed, power consumption and under all operating conditions. Statistical fluctuation in semiconductor fabrication processes leads to undesirable circuit performance. It's necessary to model manufacturing process variations to predict the device and circuit performance to minimize the impact of parameter variation on circuit performance and maximize the yield. There are different general techniques and methodologies used to handle the impact of process variation. One is worst case corner analysis, Monte Carlo analysis, design of experiments and response surface modeling, and sensitivity analysis. These are standard methods used to analyze the variability. It's really important. If we do not understand it and model it and try to minimize it, we can never maximize the yield. We always try to minimize the variability and maximize the yield. All these 4 techniques are mentioned here: worst case scenario, Monte Carlo analysis, design of experiments and response surface modeling, that is DOE RSM, and sensitivity analysis. These are the methods, analysis methods. We are done. Move to the next slide. Modeling variability. So let's talk a little bit about how variations are modeled with uniform distribution or Gaussian distribution. So uniform distribution refer to a type of probability distribution in which all outcomes are equally taken. Uniform distribution are specified with half range A. Here we have taken an example, VDD as 1 volt plus minus 10%. We are defining it as uniform distribution 1 volt and plus minus 10% here. Here half range is 100 millivolt. Normal distribution, also known as Gaussian distribution, a probability distribution that is symmetric about the mean. This is the Gaussian distribution, and this is specified with a standard deviation x. Processing variations are usually modeled with normal distribution, and circuit designer commonly treat process variations as combination of global variation and local variation. This method lumps up all the chip to chip and wafer to wafer variations into one global variation component, and the remaining variations are one local variation component, like this. We have mentioned there are global variation and local variation. So global variation, so all variations are together, global and local variations. These are interchip and intrachip. We consider all across chip, random variation, everything is included there. So circuit designer actually lumped all these chip to chip and wafer to wafer variation into one global variation component, and the remaining variation as one local variation component. And this way variation is modeled. So we try to give you an idea how process related variability, intentional, unintentionally introduced variability impact the end product, that is the chip performance. So we are done with this slide and we are done with today's episode. Thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have any question or query, please put it as a comment. If you have a dislike, also put it as a comment. Thank you again and bye for today.